This is the last bit of the last set of notes on condensation and vapor pressure. And pay attention to this because this is needed for the lab when you get back from spring break. Okay, so earmark this video, go back and look at it before the next lab that you do, because what we're going to be doing is we're going to be exploring vapor pressure using the van der Waals equation. So we've talked about equations of state, those equations that tell us about the material, the state of matter. And the ideal gas law is the equation of state that we've been working with. It's really the only one you guys know of at this point in your science career. So we're going to add a new one this morning called the van der Waals equation of state. And it has a couple of features. And if you think about this here, this looks like the this is the ideal gas law right here. Does everybody see that? nRT over V. And what van der Waals did was say, let's put in a term that corrects for the volume that the gas takes up in the room. So if you stuff enough gas in this room, eventually the pressure is going to go up, be higher than expected, higher than ideal. Why would that be? Well, because there's other molecules in the room. And if you think about pressure, it's force per square unit area. And so think of a pressure gauge on the wall. And it's the force that the molecules hit that square meter with, certain pascals, okay? If I've got more molecules in the room, they're going to bounce off those molecules before they hit the opposite wall and come back. So they're going to be hitting that square inch more often if there's more molecules in the room. In other words, we've decreased the volume of the room, so the pressure goes up. So since volume is in the denominator, if we make the denominator smaller, then the pressure goes up. So that's above ideal when we have too many molecules in the room. So this is the repulsive effect of stuffing too many molecules into a small space. So B is the term used for repulsions, to account for the repulsions of the molecules. And of course, it's a function of the number of moles of the molecule. So if you have more moles of molecules, you have a larger adjustment to the pressure. So this B is the repulsion term. We have that in the little text on the screen. Now, what about the attractions? So if we stick molecules in here at a moderate rate, and you've got a square on the wall that's measuring the force that the molecules are hitting it with, and the molecules hit another piece of molecule or another gas molecule, and they're somewhat attracted, then they're going to lose some velocity, and they're going to hit that square with a little bit less force. And so the pressure is going to go down if there's attractions in the room. And that's a function of the number of moles squared and the volume squared. And so, but this is the attractive term. So this is just van der Waals' way of adjusting the pressure in the room to account for repulsions and attractions. So the A term takes into account attractive forces of the molecule, and the B term takes into account the repulsive forces in the molecule. And then we get these pressure volume curves, these isotherms. And so these are isotherms. The ideal gas law, at high temperatures is out here. But then as you get close, you get into the condensation region, and the van der Waals equation, it's really correcting the gas behavior. When we get to the region where there's going to be condensation, the van der Waals equation fails, actually. So these funny little S-shaped curves, S on its side, these loops, are not realistic. So think about this. If we're pushing on a piston, we got a gas in this container, we're pushing on that piston, the van der Waals equation says that the pressure would rise, and that makes sense, right? We're compressing a gas, it should resist. If we're stuffing it into a smaller space, it should resist more. So we're pushing, but then the van der Waals equation has this unrealistic drop. So that would be weird. You're pushing a piston in on a gas, and all of a sudden it gets sucked in. That's not realistic behavior. What happens is it condenses, and we get a constant vapor pressure. So then we can keep pushing the piston in, and we're just condensing the liquid more and more and more and more. until it's all liquid, and then the pressure jumps up steeply. So this part, this steep rise, would be pressing on the liquid, so that seems realistic. This gradual rise would be pressing on the gas, so that seems realistic. But we need to do something with this region in the middle. And so Maxwell comes along and he says, what if we draw a line across here for the vapor pressure? So this would be P vap. So that's the pressure of the vapor above a liquid. Which is a gas. And where do we draw the line? Well, he says, let's make it to where the van der Waals area above that line is equal to the area under that line. It's kind of a nice criterion, right? And so then at this temperature down here, you might have the line, say, right here. And so then the area above that line, it doesn't really look like it's equal, but I tried. Okay. All right, so the area above that line, you would draw that line and adjust it to where the area above and the area below are equal. And so that's what we're going to be doing in the lab when we get back from spring break. So it's an Excel lab, kind of get you warmed back up. And you'll be modeling these vapor pressures for 3 different gases. So you go out in the literature, you get the A and B constants. I want everybody to do different gases. Everybody does water just to like check your work with each other, and you can see that you're all getting the same values roughly. Do different temperatures, but you'll get the same trends. And then do 2 other gases, and you'll do 5 different temperatures. So what you'll do is you'll change the temperature, the curve will move around, and then your vapor pressure is no good. And so then you got to move your vapor pressure up or down until you get the areas above and below that line to be roughly equal. So the difference between them should be 0. And then you can do it by hand for a little while, and then you let solver take over. And so we learned how to use solver in the oxygen dimer lab and the dichloroethane lab. So we'll use solver again here. So solver will move that vapor pressure up and down and check the integral and see that it equals 0. When it gets close to 0, solver will stop. Okay. So that's the lab on Monday when we get back. So check this video before lab. So this is what we're doing with that Maxwell construction in the lab. And this is the vapor pressure. Now let's talk about vapor pressure. That's the last part of this little video. We can model the vapor pressure with the Clausius-Clapeyron equation. Okay, and this is it right here. It's showing that the natural log of the pressure is proportional to the vapor, the enthalpy of vaporization over temperature. It's really over RT, right? So where did we get that? Well, e to the minus delta H over RT. It looks like a Boltzmann distribution, and it is. So there's a certain amount of energy that it takes for a molecule in a liquid to have before it escapes the surface. And so this Clausius-Clapeyron equation is sort of measuring the pressure, which the pressure is a proxy for the equilibrium constant. So this is a 2-level system, evaporated or not. And does it have enough energy to evaporate? Well, that's the enthalpy of vaporization, is that energy. So we put enough heat in there, the vapor pressure climbs because it's scaled with that RT, and we're increasing the Boltzmann probability that we would have a gas molecule. Okay, so how well does it do? Well, it does really well. So this is the gas constant, R, times the natural log of P over the triple point, temperature for water. And this is 1 over T, this difference. And sometimes you'll see a minus sign in front of the delta H of vaporization here. And all that means is that these two are swapped. So if you swap these two, then you get a minus sign here. Or if you swap these two over here, you get a minus sign. So you got to pay attention, very careful, between which is the star and if there's a minus sign or not. And so the way I've written it here works well. So star on bottom here, star in front there. And this is just your reference temperature and pressure. You can use any one of these. The boiling points are the most convenient, I think, to use because by definition, a normal boiling point has a pressure of 1 atmosphere. That's why it's boiling. It's creating enough vapor under the liquid that those bubbles have a 1 atmosphere pressure and they can sustain their cavity nature until they reach the surface and pop and release the gas. So we see that. And so you can look up tables of boiling points and you can get this P star and T star. P star for a boiling point would be 1 atmosphere. And then you could calculate all the other pressures in terms of their atmospheres. But look how good this is. This is 3 points across. Look how big a temperature range. So this is a huge temperature range. And yet it's still a really great linear trend. That's really very good. So the Clausius-Clapeyron equation is great. All you need to know to calculate vapor pressure is the boiling point, so the temperature. If you know the temperature of boiling, then you know this one is 1 atmosphere. Boil. And then you need to know the delta H of vaporization. Now what y'all are going to do is you're going to be calculating this in the lab. You'll be putting in the temperature, calculating it, and then you're going to plot R ln P versus 1 over T, and the slope will be this delta H of vaporization. So for your gases, that'll be the last part of the lab. You'll do 5 different temperatures. You'll plot R ln P divided over 1 over T, and then the slope of that line will be the delta H of vaporization. And then you'll compare your delta H of vaporizations to the literature. So for your gas, you need to look up the A and B constants for your gas and then try to find the delta H of vaporization for that gas. So here's, if we don't take the natural log of that, this is what it looks like. So the atmosphere, it goes up in an exponential manner, right? So you can see this very little change in the pressure from 300 to, see, what is this, 273, so, very close to freezing to boiling, but then it continues to go up to the critical point. And so that's the dramatic change in vapor pressure. If you were to take the log of P and just plot it versus temperature, it's not linear anymore. It's linear to 1 over temperature. And so this is what we get. This is the PVAP table. If you look up the vapor pressure, like on CHEM, on the CHEM web book with NIST, you would see these points fall pretty well on the line. And then lastly, let's talk about the Antoine equation. So you might look up a vapor pressure equation in the CRC and see a totally different equation. We're talking about the Clausius-Clapeyron equation, and it gives you a very good plot. Here's the plot for water. And then here's the Antoine equation. And so you would find these A, B, and C constants. And this is typically in log base 10. So you need to be sure to know if you're dealing with natural log or log base 10 of pressure. And so this Antoine equation, you would have the A, B, and C constants listed in the reference book that you're looking for. And these are not exactly the same, but they're good. A lot of times the Antoine equation, these empirical constants, tuned for a specific range. Okay, so they might be for the, maybe the naturally condensed range of water between freezing and boiling. Okay, and so then when you get up to the higher temperatures, they might be off because the A, B, and C constants were tuned to those regions, but they'll be very accurate for those regions in which they're tuned. So that's a little bit about vapor pressure. This is the one equation that I've used outside of academia. Whenever I was in industry, they were asking us to determine if the vapor pressure of glues and so on would reach the point where it would incapacitate people working on the production line. Okay, and so we had to calculate the vapor pressure at saturation for the large room that they were in. So, if they were going to be incapacitated at, say, 1% concentration in the room, we did the ideal gas law and figured out what 1% would be in terms of the number of moles of molecules of solvent in that room. And that was a huge amount. Then we had to see, would we ever get that from the vapor pressure? What temperature would we have to get that much pressure in the room, and how many moles we needed to incapacitate them? So the little tube of glue didn't have enough solvent in it to reach, even if all of it evaporated, it instantly to reach the incapacitation point for a worker. Okay, even though you could smell it, it wasn't anywhere close to making you pass out. Okay. And so we were able to show with the Clausius-Clapeyron equation that was not going to happen. Also, our exposure to chemicals is through inhalation most of the time. You're dealing with organic solvents, and so this equation is very important for calculating the parts per million of the molecule that's in the air. So this is a very common calculation to do.